So another example using Faraday's law is that we can think about our slinky solenoid or an ideal solenoid. This is not, because this isn't, you want the wires more tightly packed. But you can have a current that runs through this, but you could plug it into the wall so it would have 60 hertz signal. So you could have I that's a function of time. So I is no longer still, it's changing with time, and our magnetic field in the middle, with this setup, it looks to me like in the middle, my magnetic field is going like that with that current. And if the current changes, if it goes from up to then down, right, if it's oscillating, if the current is going up and down from, and there's 0, right, then the magnetic field's going to be switching back and forward, back and forward. And so if we put a loop right here, we can of course get some induced current on that loop. And so I want to do a quick calculation of how we might find that. So we want to ask, what's the induced current? Induced current on the small loop on the inside, right? So this loop here that has a radius little r. And that's going to be much smaller than solenoid because I want to be where the magnetic field is basically uniform even though it's changing direction, right? So we've got the same magnetic field all the way across this surface. It just keeps changing back and forth. It gets bigger and then it gets smaller, goes away, and then gets bigger and smaller and goes away, and it just oscillates back and forth like that. And it oscillates according to this. So if we look at that, the flux through the loop is going to be the B due to the solenoid times the area of the small loop, pi r squared. And so the induced EMF, or the induced voltage, is just going to be derivative of this flux with respect to time, which would be, we have a pi r squared, the area is fixed, dB dt. Now in this case, our I is going to be given by I is equal to some peak value, I peak. Peak value, let's say that looks like a sine, could be sine or cosine, doesn't matter. Sine of 2 pi times the frequency times time. And frequency is 60 hertz here. Okay, so that is my current as a function of time, which means when I put that current as a function of time right into this equation, that tells me how my magnetic field varies with time. So I get B is equal to mu naught times n, the number of loops per unit length, times then I peak sine of 2 pi frequency times time. All of it's the sine of all of that. And so all I have to do is take my derivative of that. And I wanted to point this out just to remind you that when we take derivatives like this, we're going to take derivative with respect to time of mu naught n I p sine of 2 pi f t. So in my derivative, my mu naught, my number of loops per meter, and my peak current, because that's whatever this maximum is, are all constants. So those can come out. So I'm just taking the derivative of sine. So this becomes pi r squared mu naught n I of the peak. And then I've got to take the derivative of this with respect to t, but that means I've got to take the chain, I've got to do the chain rule, right? So derivative of sine of 2 pi ft dt means I take derivative of sine, so that gives me a cosine, 2 pi ft, times, this is a chain rule, the derivative of what's inside, 2 pi ft with respect to t, and that's a pretty easy derivative because, again, these are all constants, and so the derivative of t with respect to t is just 1. So this altogether just gives me a 2 pi times the frequency. So putting all of those back together, this becomes pi r squared u naught n I peak times 2 pi times the frequency cosine of 2 pi ft. And so that is my voltage, my EMF. So if I want my induced current, it's equal to E over R, or all of this over R. So the induced current is going to be oscillating up and down, but it's going to be a cosine relationship. So if I were looking at the same kind of thing, and actually it would be a negative, depends on which way we do it, but it's going to be a little bit out of phase. So this is a sine wave, this is current on the solenoid, and then on the loop we probably have a smaller current, and it would be like that. It would be in an opposite direction to oppose the change here. So this would be the current in the loop as a function of time. Same frequency, just a smaller, sorry, it doesn't show up, a smaller amplitude there. Okay, and the amplitude, this peak distance, would be given by all of this stuff right here in front of the cosine term. So that's just another example of how we can use Faraday's law, and then this minus sign right here for it to be upside down, because this is the absolute value of the current, from Lenz's law. But all of this together is just another example of how we just use this and pay attention to what is changing with time and what is not. And we can get some information about induced information. This is what we would call a pickup coil. It's a pickup coil. And it's got some applications as well in terms of having oscillating current on wires and then having coils that pick up the signal.